Bonjour, mesdames et messieurs. I'm afraid I have to start with a disappointment for all of you guys because my French is not very good anymore. So I have to admit I learned 5 years long French in school, and I believe I forgot at least 4.5 years of that. So that's the reason why we will continue in English. Makes it much easier for me, and I believe also much easier for you, because if I would do it in French, it would end up in a mess. So, Adva Optical Networking, so we're happy to be here. It's the first time we are at this event. For those who don't know Adva, so we're a company, we're a vendor of optical and Ethernet access solutions. So we're quite a while around in the market. In fact, it's the 20th anniversary this year. So we're around since 1994. And we have quite some traction in the meantime in the inter-exchange business. So you probably know DKIX, you most likely know AM6. So those are good customers of ours and quite some others. And because we're an optical company, I was asked to talk about WDM networking fundamentals. I thought, hey, cool thing. I have a very nice presentation already ready, nothing to do, just come here and talk about it. Then I talked to Sulen, and she told me, that's too basic. I have a lot of optical experts in the audience, would not work. So I was in trouble, and this is why maybe this title is not the best one. This one is a better one. What the heck is DP-QPSK? Maybe a question first. Who is an optical expert here in the audience? Okay. Oh, one. Oh, that's an Adva guy, doesn't count. Who considers himself to be an optical expert, knowing he is none? Good, so I'm in good company. No, I hope I understand a little bit of it at least. Good, DP-QPSK, during my presentation, we will all learn what is behind that. What is it? And it's about modulation formats at the end. But just to get all of us on the same page, let's start a little bit with basic optics. So optics means transmitting data using the light over fiber. And here we see the optical spectrum. So the colored one, this is what we see. So it starts with infrared and goes up to the shorter wave. Where we transmit data over the fiber, it's quite a different piece of the spectrum. That's where we see the windows here. The first, the second, third window, we'll come to that. And this clearly first explains why we don't see a lot if we look into the fiber. And in fact, if we look into the fiber just to try to see something, we would be blind. So we won't see anything in the future. So don't do that. Optics, WDM, is a very simple technology. The only thing we are doing is we are transmitting light using different wavelengths, different frequencies over the fiber. So we call these colors, even so knowing very well we can't see these colors. Combining them, transmitting them over the fiber, and then splitting them up just to reuse the fiber multiple times. Very easy concept. We have two issues when we are doing that, two things we need to fight. The first one is called attenuation. So if you transmit light over a fiber, it's like transmitting light or sound over the air. It gets weaker and weaker the further you're away. So that's the absorption we're having in the fiber. But there's a second thing, which is called Rayleigh scattering. It's basically photons running through the fiber. They get deflected on small atoms, which is also attenuating the signal. So we need to cope with that. We need to find ways to transmit light through the fiber with as little attenuation as possible. The second issue we are facing is called dispersion. So what is dispersion? If we are transmitting light in very sharp pulses, like on the left-hand side here, through the fiber, they get smeared, they get broader. Because some frequencies are traveling faster, some frequencies are a little bit slower, so it smears. And this dispersion has two components. So one component is very dependent on the wavelength, so the frequency of the signal, and the other one is depending on the medium, the fiber. So this is also something we need to deal with. So the longer the light travels, the more it gets smeared. And there are techniques, modulation techniques, which help a little bit. So we will come to that. But there's even more. There are things we call nonlinear effects, like Brillouin scattering, Raman scattering, self-phase modulation, four-wave mixing, and many others, which are a little bit of a mess if we transport light through a piece of fiber. We'll see what this means. So that's the basics for today. I want to talk a lot more about this. This is an important figure here where I would like to explain why we talk about these modulation techniques and why we invest so much on the technology side here. So the first thing is, if you look at this curve coming from the left-hand top to the down there, so this is the attenuation curve because of Rayleigh scattering, because of absorption. So you see the first window on the left-hand side, it's the 850 nanometer window. So within data centers, within offices, this is used very often. This was also used at the beginning of optical transmission because it's easy to build something from a technology perspective. But it doesn't help a lot. You can see attenuation is very high in this window. And there are also other problems with it. This is why it's still used only in-house, but it's cheap. So a couple of years later, industry figured out how to do the same in the 1310 nanometer window. That's the second window. It's cool because you can travel already longer distances. So it can go up to a couple of kilometers maybe. It's lower attenuation there. But there's a fundamental issue in this window because you can't do WDM, so multiplexing multiple wavelengths there. There are too many effects which are disturbing it. And this is why some years later we came to the third window, which has a C-band and an L-band, attenuation even lower, technology even more complex. But today we can handle this. And we can do a lot of cool things on the WDM side because dispersion is okay, attenuation is okay. So this is where we're talking about. Now, if you remember this huge spectrum we had at the beginning, we can only use this little tiny bit of spectrum when transmitting light over fiber or data over fiber. And this is the fundamental issue here. And this is the reason why the industry talks so much and develops so much and invents so much in terms of modulation techniques. Good. Now, you can see it's kind of complex because suddenly there are formats out there called PMRZ QPSK. So totally confusing for all of you, also for me, partially. So modulation format means a very simple thing. We're receiving data, might come over fiber, might come over copper. Then we are regenerating it, might be in a switch, might be in a WDM system, might be in an OTN system even. And then we are shaping it and transmit it over a dedicated frequency, wavelengths, and we modulate it in a very specific way that we can get a lot of data over a very limited amount of spectrum. And this is what I want to talk about today. Good. So first question is, why is it so complex, and why do we talk about these complex modulated optical signals? Very easy to explain. The reason is spectral efficiency. Spectral efficiency means how much data can I transmit over the available piece of spectrum. So if you look at the top line of the figure, this shows us three channels of a spectrum, 50 gigahertz of spectrum each, so the red one, the green one, the blue one. And if you use 10 gigabit transmission with what we call on-off keying means if there's a 1 bit, we send light. If there's a 0 bit, we send no light. So just on and off. Then this fits nicely into this channel architecture there. So in each of those 50 gigahertz channels, we can easily transmit 10 gigabits per second. If we move on to 100 gigabits, we have a small issue there. Because first, transmitting 100 gigabit over 50 gigahertz, it's already twice as much. Sounds difficult. Second, it doesn't fit anymore into this channel width. So it moves over, it creates distortion in the other one, it creates interference in the other channels. Then if we have filters in there which cut the spectrum into channels, then some of the information is lost. So clearly, in a 50 gigahertz grid, transporting 100 gigabit signals using on-off keying, definitely not an option. It will not work. On-off keying was used in the past because it's simple hardware. It's wide spectrum. Yes, there's a little bit of drawback there compared to newer technologies, high dispersion impairment, but this was solved by using dispersion compensated fiber. Now, what can we do in order to make this work? Keep the 50 gigahertz grid and get 100 gigabit into a 50 gigahertz channel. So we're using something new modulation format, and we want to talk about today about QPSK, which suddenly makes the 100 gigabit fit into the 50 gigahertz. So sounds like a magician, sounds like a lot of magic, but it isn't. It's a lot of mathematics. It's a lot of physics, but you will understand very easily what we do there. So it's nothing new, because those things we're doing now on the optical side, those are things we're doing since quite a while in the radio transmission segment. Why did we do it there earlier than in the optics? Very simple answer, because the frequencies are much lower, and this means technology is much easier to handle. So if we talk about a few kilohertz, for example, or maybe a few megahertz, or maybe even a gigahertz, it's easier to build this stuff than talking about 100 gig or even more. So this is why we applied these tools in radio transmission and some other segments much earlier. What we're doing here is a very simple thing. So we're not using on-off keying anymore. Remember, sending light, 1, sending no light, 0. We're using now basically all the parameters we have for a light wave. So we not only have the frequency, which is the wavelengths, we can also talk about the amplitude. So it's not only on and off, it might be something in the middle. And then there's something like phase, so phase shifts and so on we can look at, we'll see that. We can talk about different things like polarization multiplexing, very easy thing. If we send a light signal through a fiber, then it has all the polarizations if we do nothing. So it oscillates like this, so you can't read a lot from the polarization. But you can filter it, and you can use 2 dimensions. You can use vertical polarization, so it oscillates only up and down, and horizontal. And suddenly, we have 2 signals already on 1 wavelength. And then we use some pulse shaping filters in order to make it a little bit sharper. So we are using a lot of different things, and we will learn how we do that. So this figure illustrates basically what we're doing. So the red part of it shows on-off keying. The gray bar in the middle shows our 50 gigahertz of spectrum we have available to transmit, and clearly by using on-off keying, we are far off. Much too wide, can't do this, interfere with the other channels. Now, if you use QPSK instead of on-off keying, we'll explain that in a minute, then we can already narrow this a little bit. A little bit in this case means by a factor of 2. If we use polarization multiplexing, DP stands for dual polarization, then we can narrow it even further. Also, again, a factor of 2. And if we use some pulse shaping filters, we really fit it into this gray bar, so in our spectrum. So that's basically what we're doing. And that's basically the reason why we need complex modulation schemes to get a lot of data across the fiber. Good. Does this mean we can do a lot of fancy things and there's no limit if we use all the parameters a light wave has? No, definitely not. There are 2 limits, very hard limits, we cannot exceed. So the first one is called the Shannon limit. So Shannon, a guy at the beginning of the 20th century, so he found a formula which is valid for all transmission over any media, and it basically says the channel capacity is limited by the bandwidth, so the spectrum we have, in our case 50 gigahertz, and it's also limited by the signal-to-noise ratio. So the larger the signal-to-noise ratio is, the more we can have. The lower it is, the less we have. So how can we increase channel capacity then? One is increasing the bandwidth. That's what we don't want to do because we want to get more into the spectrum. And the second one is working on signal-to-noise ratio. So working on signal-to-noise ratio can be 2 things. We can build better filters, better amplifiers, all of them introduce noise, better lasers with less noise, so that's what the industry is doing. Or we increase the signal power. Unfortunately, if we increase the signal power, we have another problem because we're running into those nonlinear effects. You can see it on the right-hand side with the 2 graphs there. So one is for linear detection, the other one for coherent. We'll see this as well. So the blue line or the green line means it's all cool, nothing happens if we increase the launch power, so we get more data over the spectrum. But unfortunately, if we reach a certain power level, it goes down because of those nonlinear effects. So they're much more severe if we have a higher power. And this clearly limits the signal-to-noise ratio we can achieve. And this clearly limits the whole thing at the end again. So Shannon limit is what we have to deal with. And just as an idea, with DP-QPSK, what is used for 100 gig transmission today, we are already very close to the Shannon limit. So there's not much room there. Okay, so now let's talk about QPSK. What is QPSK? And basically what we want to do is we don't want to code single bits and transmit it as a signal over the fiber. We want to code symbols which contain multiple bits here. For example, the blue ones are 2 zeros. And we say, okay, this is symbol B. The red one is 1 and 0. We say this is symbol D. Same way, A is 1, 1, and C is 0, 1. So instead of having single bits coded, we code 2 bits in a symbol already. That's the idea. And we can do even better. So we could think about modulation schemes where we code 8 or 16 or even more bits in a single symbol. But in order not to make it too complex, let's start with the 2 things here. So now it gets a little bit more tricky for you guys. Who has a degree in mathematics or physics? 1, 2, 3. Okay, so I'm in good company because I don't. So you might need to help me a bit, but let's see. So what is light? Light is, as it's called, a transversal electromagnetic wave. So just an electromagnetic wave, and every electromagnetic wave can be described by this formula there. So our wave E can be described, let's look at the middle piece here. And this has basically 4 parts, 4 degrees of freedom. The first one is the frequency in here. Frequency, that's our wavelengths. So we can change the wavelengths, and we do this in a 50 gigahertz grid. So that's a simple thing, and I guess a lot of you know this already. But we can do this polarization thing, which gives us 2 degrees, which allows us to double the data. Because remember, one is oscillating in this direction, the other one in this direction. Both have the same wavelengths. Cool. We double the capacity. Then we can move on and can say, instead of just 1 and 0, so light on, light off, we can talk about variable intensities, variable amplitudes. So we turn the light a little bit on, a little bit more, or fully on. So we have a little bit more freedom suddenly there. And this might be a significant gain, as we will see. And then there's a 4th thing, which is called phase. And light is oscillating. And now if we shift the whole thing a little bit, then we talk about a phase shift. So that's a parameter in there. So if we shift it by 2 times pi, so the whole circle, then we are at the same thing where we started. So we basically have 2 times pi in one way or the other to use. Good. So we use all of these degrees of freedom to move on. I have to smile now. Good. You're welcome. Good. And in order to make it a little bit simpler to understand for all of us, we talk about constellation diagrams. So remember, the first part of the equation we just talked about, the whole thing is shown in polar coordinates. So we express our signal in terms of the amplitude, so that's the intensity, and phi, the phase shift. To make it a little bit easier to understand for us, even if the complex plane is a rather complex thing, we can also show it, as shown in the second part, it's the lower equation here, in terms of the real part, or the in-phase part, and the imaginary part, or the quadrature part. So this is what we see on this diagram. The real part is the I-axis, the Q-axis is the imaginary part. So if we transmit a signal, like our green dot here, then we can either describe it by E, the amplitude, and phi, the phase, or by Q and I in the complex plane. So those 2 parameters. And what we can do is we say, okay, each symbol, remember the A, B, C, D we had before, corresponds to 1 dot in this diagram. And by doing this, we can do QPSK. Basically, we have 4 symbols, the 4 black dots here, A, D, B, C, different order. And depending on whether we want to transmit A, B, C, or D, we use a different phase. So we shift the whole signal by a certain amount. QPSK still uses the same amplitude for all the symbols. So you can see they're all in the circle. So the distance from the crossing point in the middle to the points, the symbols, is the same distance. So that makes it a little bit easier. But suddenly we get 4 symbols coded basically in 1 hertz. So they differ in phase, but not in amplitude. And this gives us a gain of 2, because we can code 2 bits by just sending 1 symbol. Understood? Okay. Then let's make it a bit more complex. No, just to resume first. DPQPSK, what does it mean? If you want to transmit 100 gigahertz and do nothing, just do on-off keying, we need 100 gigabaud. So frequency of 100 gigahertz, basically. If we use polarization multiplexing, we can halve it, because we have the vertical dimension and the horizontal dimension the light oscillates. If we use QPSK on top, we can reduce it again by a factor of 2, because we can transmit 2 bits in 1 symbol. Fantastic. We end up with 25 gigabaud, which fits excellently in a 50 gigahertz grid. So that's simply the art behind getting the 100 gigabit per second into the 50 gigahertz grid. Polarization multiplexing and this advanced modulation format, where we consider the phase on top of the signal. Amplitude, still the same. But of course, we can do much more. And if you look at some of those constellation diagrams, on the left-hand side, we can start with on-off keying. So that's a simple one, light or no light. Basically, the red dot can lie everywhere on the outer circle, because we're not looking at the phase at all. Good for 10 gigabits per second, gives us a spectral efficiency of 0.2 bits per second per hertz. Was okay in the past. We can do a bit better if we use BPSK, which means binary phase shift keying. So it's just 2 symbols there. It's not a lot of gain in terms of capacity there, because it's still just 2 symbols, like in the on-off keying model. But those 2 symbols are now much further away than in on-off keying. What does it mean? The further those symbols are away from each other, the more noise I can have and can still recover the signal. And this is why BPSK is used very often in undersea cable, because it can travel longer distances. It's more complex to build, yes, but it gives you either higher capacity, like for 40 gigs, or it gives you a much easier way to cope with these, not the attenuation, but the dispersion things and other effects. So, and the spectral efficiency, if you use 40 gig in a 50 gigahertz grid, is already higher, 0.8. Now let's move on to QPSK. We just discussed it. We have 4 symbols here, still the same amplitude, lying on the same circle, 4 different phases, gives us already 2 bits per hertz, so 10 times better than on-off keying. Typical for long distance and medium distance 100 gig transmission. Now we can go on. The next thing we could do is move a little bit away from this phase shift keying, which only uses 1 level of amplitude, but also play a little bit with the amplitude. So there's what we call QAM, Quadrature amplitude modulation. 8 QAM has 8 dots, 8 symbols, allows us to code 3 bits, which means 3 bits per second per hertz. And we have basically 2 amplitude levels and different phase levels there in this case. It's a modulation format which is not so common, but it's used here and there for 200 gigabit signals. What's much more common for moving to 400 gigabit is 16 QAM. Now, we also stop using this, the same amplitude levels there, so moving away from these circles, but go into a lattice format there. Makes it a bit easier, because suddenly the dots have the same distance between each other, which allows us to reduce noise a little bit and to detect them easier. And it gives us 4 bits per hertz. So we can transport 4 bits with 1 symbol, and can detect it on the other side by looking at the phase and looking at the amplitude. And of course, the wavelengths and all the other stuff we do. And we can go on. So there's not only 16 QAM, there is 256 QAM, there's 1024, 2048 QAM in radio technology today. So at some point, we will see this in optics as well. Today, capacities are so high that these techniques are a little bit difficult to build because of all the signal processing we need for that. Good. The issue we have, and you can see it here, the further we move from the left to the right, the closer those dots are. And the closer they are, the more difficult the symbol is to detect. Because if we have some distortion in there, if we have some nonlinear is there, the signal we detect might move a little bit, which means getting closer and closer and closer reduces the capability to detect the correct signal. And this you can see here, if you look at the green triangles, for example. On the right side, we have QPSK, which can go distances, theoretically at least, up to close to 4,000 kilometers, has a spectral efficiency of 2. If you do 8 QAM, we have a spectral efficiency of 3, but we are limited to 1,500 kilometers already, because the dots are much closer to each other, and it's much harder to detect the right signal. If we go to 16 QAM, it's even more difficult, so we end up somewhere in the range of 1,000 kilometers. Theoretically. Practically, it's a different thing. Practically, it's maybe a few hundred if you're lucky. But we have a higher spectral efficiency. So it's a trade-off between the distance we can bridge and the capacity. And this is why we are talking today about modulation schemes, or not modulation schemes, implementations where the modulation scheme can be adapted. So you can use the same module, the same transponder. If you need it for a long-distance transmission, you go to a lower modulation scheme, like QPSK. If you need it only over short distance, you go higher up, maybe 16 QAM, and get 400 gigabits over it, over the same spectrum, instead of the 100. So that's where the industry is going. Good. The big question is, which scheme fits to my application? So clearly we have seen that distance is a big question here, but there are others. So first, of course, it's the occupied spectrum. If I have a lot of data and if I have terabits to transmit, of course, spectrum is very, very valuable. If I only have 100 gigabits, then maybe I waste a couple of wavelengths, use simpler technology, maybe occupy more channels at a lower capacity, and therefore save a lot of cost. So it's a question, how much do you need at the end? Dispersion tolerance, reach are also questions. So we just have seen that. If you want to go further, then maybe we have to lower the thing a bit. Dispersion tolerance, we'll see on the next slide. There's also an interesting thing to handle that one. Of course, it's technical feasibility and cost, which plays a significant role. And then it's also a question about the existing infrastructure. So what do you have already in your infrastructure? What filter structure? Does it work with the stuff you have already? Is it compatible, or do you need to do fancy things? So there are a lot of questions there, but there's always a right choice, which is perfect. So if you have shorter distances, then typically you go to higher modulation schemes. You maybe even go to a different detection way than the fancy stuff you need for long distance. Good. So we talked a lot about transmitting the signal. What we also have to talk about is detecting the signal. When we used on-off keying in the past, it's very simple to detect the signal, because when there's light, 1. When there's no light, 0. Very easy. We didn't have to care about phase. We didn't have to care about amplitude and those things. Not a problem at all. Now, if we do advanced modulation schemes, where we also modulate the phase, we have a problem, because we need to be able to detect the phase. And we can only detect the phase if we have a reference signal. Otherwise, we have no idea whether it's shifted now by pi half, or pi, or 2 pi, or whatever. So we need some kind of reference. And this is something we do today, especially for the 100 gigabit stuff, with something called coherent detection. Coherent detection is a very simple thing, because you produce the same signal at the receiving side. You superimpose it to the signal you receive. And it has 2 fantastic benefits. The first one is you can detect the phase changes, because if the phase changes, when you compare it to your signal, you can see that. And second, if you modulate the signal with the same frequency over your receiving signal, you're canceling out all the other frequencies, and you're amplifying the frequency you want to see. So it acts like kind of an amplifier. And this is why this is used in 100 gig, and this is why the DP-QPSK has much more tolerance in terms of dispersion. Because remember, it gets smeared, so the frequency gets wider, but now at the receiving side, you're just looking at the thing you want to see, and you're canceling out the other stuff. So that's one way of doing it. A bit complicated, a lot of digital signal processing. That's why 100 gig coherent is exciting technology coming at an interesting price point. So it's a bit more expensive than 10 gig. There's also other ways in order to figure out the phase, and one is called differential phase shift keying. So what are we doing here? So basically, instead of coding the symbols, the bits with the symbols, so a symbol for every bit, let's just use 2 bits here, so one symbol for 1, one symbol for 0. We're only coding phase changes. So if you move from a 1 to a 0 or a 0 to a 1, for example. If we do that, and if we do another fancy thing, which is at the receiving side, we look at the signal, and we delay the signal by 1 circle, so 1 bit basically, and then superimpose both of them, then all the zeros get canceled out, so we don't see anything, and all the ones show us a signal. And the signal is even stronger because it amplifies. So using this interesting technique, we can easily figure out where are the ones and where are the zeros without coherent detection. But still, this is more complicated and more difficult to build than the on-off direct detection where you just look at light on, light off. But if you want to use more complex schemes here for modulation, we have to go through that. Good. So far, so good? Everybody happy? Something learned or too complicated? My colleague asked me I should also talk about security. So we in Adva talk a lot about security since a few years. It became much more intense when this whole NSA thing came up, especially in Germany with Ms. Merkel and so on, getting more or less hijacked by the NSA. Security is important. Now, if you look at all those modulation stuff and imagine you run the signal with all this fancy technology over the fiber, you might think, if you tap the fiber, you can't read anything because you need to have fancy technology and a deep understanding about all these things in order to read the bits. It's not really the case because this technology, you can buy basically the same stuff your victim has on the other end, and then you can try to do something. And there are ways of tapping the signal. Because if you look at the fiber path, which is running through a metro, it's often running through street cabinets, so you can open them and tap it. There are often Y bridges here and there for service activities, splice boxes, coupling devices. So there are ways to gain access to the fiber. And if you're an expert, yes, you might tap it, and you might read the data. It's not so difficult if you work in high-frequency trading because the time you read the data, it's already expired, so it doesn't help a lot. But it's very interesting if the victim is a bank, insurance company, so financial vertical, government agency, military. So there's quite a kind of a panic in the market right now, and we have this encryption stuff in our product, and everybody wants it. Very interesting. Good. So what do we do, basically? So if we connect to data centers today, then there's a lot of security for the data center itself. So there's physical security. So you can only get in with fingerprints. There are huge walls, fences, whatever. Then within the data center, the hardware, the software, everything is protected. So there are firewalls, everything is in there. But if we don't do nothing on top of that, as soon as we leave the data center and go, for example, to the backup center on the other side, everything is open again. And if we tap the fiber, we can read the stuff. Fantastic. So, and this is why we built an encryption solution into our optical transport solution. So it's completely built in there, and it has 3 components. So the first one is a cipher, which is basically encoding the data. So what we do here is AES 256. So that's the strongest you can do today. And it takes a long time to decipher it. The second thing you need on top is a secure key exchange, because it doesn't help a lot if everybody knows the keys, because then you can listen again. And here, the algorithm of choice is called Diffie-Hellman. So it's a dynamic key exchange where you have a shared secret. It's a little bit like PGP. Some of you might know that. And also, the keys are changed in a periodic way. So every 5 minutes, 10 minutes, whatever you want. And then, of course, you need a little bit of authentication in there. You need to have restricted access, all those things which are typical in order to make it a secure solution. And by implementing those things in a very dense and cost-effective way on a WDM platform, you can easily secure the connectivity between the two sites. And this is where the world is going today. So it gives us a high security also on the transport path, has very low latency, which is very important, can go up to 100 gigabits, can go up even further if you want. And it will be needed more and more. So we have more cloud, we have more dynamics. We talk about SDN, functions virtualization, all those things. So everything will get more distributed, which means we need more security in our networks. But this brings me to the end. And thanks for your attention. I hope that you learned something. I got some smiles, I got some nods. So at least some of you felt it was useful. Thank you.
Any questions?
I've got a sort of a technical question, if that's okay.
Yeah.
So you're only changing the polarization. Yeah, hi, John Hill from IX Reach. So at the moment, it looks like you're only using 2 polarizations for the light. Mm-hmm. Is there any limit on how many different polarizations you can actually have in the future?
In theory, there's no limit, of course. You can use different angles. The challenge is detecting it.
Right.
Because you need some filters, some digital signal processing to detect the polarization. And the closer your polarizations are to each other, the harder it becomes to detect. And this is why the industry today is working with 2 polarizations. But of course, if you look maybe 5 years, 10 years into the future, it might be 4, it might be 8. So there's no limit. Yeah, it's just a matter of detecting it.
Right, I thought so. I guess 16 QAM, started off, as you rightly said, as just two different phases, and now it's at 16 with amplitude as well. So
yeah,
I guess that's the future.
Yeah,
thank you.
Exactly. You're welcome. Anybody else? So I'm always around in the breaks the whole day. So if you have further questions, just let me know. Thank you.